Principal components analysis. In projection methods, we are interested in finding a mapping from the inputs in the original d-dimensional space to a new k less than d-dimensional space with a minimal loss of information. The projection of x on the direction of w is z equals to w transpose times x. Principal components analysis PCA is an unsupervised method in that it does not use the output information. The criterion to be maximized is the variance. The principal component is W1 such that the sample after projection onto W1 is most spread out so that the difference between the sample points becomes most apparent. For unique solution and to make the direction the important factor, we require that W1 whose absolute value is equals to 1. And we know from equation 5.14 that if Z1 is equals to W1 transpose times X with covariance of X equals to sigma, then variance of Z1 is equals to W1 transpose times the summations of W1. And we seek W1 such that the variance of Z1 is maximized subject to the constraints W1 transpose times W1 is equals to 1. And writing this as a Lagrange problem, we have that the maxima of W1 transpose times the summations of W1 minus alpha times W1 transpose times W1 minus 1, where the maximum is taken among all possible W1, and taking the derivative with respect to W1 and setting it equals to 0, we have that 2 times the summations of W1 minus 2 times alpha times W1 is equals to 0, and therefore the summations of W1 is equals to alpha times W1, which holds if W1 is an eigenvector of sigma and alpha, the corresponding eigenvalue, because we want to maximize W1 transpose times the summations of W1 is equals to alpha times W1 transpose times W1, which is equals to alpha. And we choose the eigenvector with the largest eigenvalue for the variances to be maxima. Therefore, the principal component is the eigenvector of the covariance matrix of the input sample with the largest eigenvalue, lambda 1 equals to alpha. The second principal component, W2, should also maximize variances be of unit length and be orthogonal to W1. This later requirement is also that after projection Z2 equals to W2 transpose times X is uncorrelated with Z1. For the second principal component, we have that the maxima of W2 transpose times summations of W2, where the maxima is taken among all possible W2 minus the following terms, minus alpha times W2 transpose times W2 minus 1, then minus beta times W2 transpose times W1 minus 0. So taking the derivative with respect to W2 and setting it equal to 0, we have that 2 times the summations of W2 minus 2 times alpha times W2 minus beta times W1 is equals to 0. Pre-multiplied by W1 transpose, and we get 2 times W1 transpose times the summations of W2 minus 2 times alpha times W1 transpose times W2 minus beta times W1 transpose times W1 is equals to 0. And note that W1 transpose times W2 is equals to 0 because they are orthogonal to each other, and W1 transpose times the summations of W2 is a scalar equal to its transpose W2 transpose times the summations of W1, where because W1 is the leading eigenvector of sigma, that is, sigma W1 is equals to lambda 1 W1. Therefore, W1 transpose times the summations of W2 is equals to W2 transpose times the summations of W1, which is equals to lambda 1 times W2 transpose times W1, which is equals to 0. Then beta is equals to 0, and equation 6.8 reduces to the summations of W2 is equals to alpha times W2, which implies that W2 should be the eigenvector of sigma with the second largest eigenvalue lambda 2 equals to alpha. Similarly, we can show that the other dimensions are given by the eigenvectors with decreasing eigenvalues. Because sigma is symmetric for two different eigenvalues, the eigenvectors are orthogonal. If sigma is positive definite, that is x transpose times sigma times x greater than 0 for all non-null x, then all its eigenvalues are positive. If sigma is singular, then its rank, the effective dimensionality, is k, with k less than d, and lambda I starting from k plus 1, k plus 2, and so on until d are 0. Lambda I are sorted in a descending order, all those eigenvalues, and the k eigenvectors with non-zero eigenvalues are the dimensions of the reduced space. The first eigenvector, the one with the largest eigenvalue W1, namely the principal component, explains the largest part of the variance. The second explains the second largest, and so on. Now we define Z equals to W transpose times x minus m, where the k columns of W are the k leading eigenvectors of S, the estimator of to sigma. We subtract the sample mean m from x before projection to center the data on the region. After this linear transformation, we get to a k-dimensional space whose dimensions are the eigenvectors, and the variances are over these new dimensions are equal to the eigenvalues. See figure 6.1. To normalize variances, we can divide by the square roots of the eigenvalues. Figure 6.1. Principal components analysis centers the sample and then rotates the axis to line up with the directions of highest variance. If the variance on Z2 is too small, it can be ignored and we have dimensionality reduction from 2 to 1. Let us see another derivation. We want to find a matrix W such that when we have Z equals to W transpose times X, assume without a loss of generality that X are already centered, we will get covariance of Z equals to D prime, where D prime is any diagonal matrix. That is, we would like to get uncorrelated Zi. If we form a D by D matrix C whose ith column is the normalized eigenvector Ci of S, then C transpose times C is equals to identity, and S equals to S times C transpose, which is equals to S times C1, C2, C3 until CD times C transpose, which is equals to SC1, SC2, C3, and so on until SCD times C transpose. That is equals to lambda 1 C1, lambda 2 C2, lambda 3 C3, and so on until lambda D CD times C transpose. That is equals to lambda 1 C1 C1 transpose plus lambda 2 C2 C2 transpose, and so on, plus lambda D CD CD transpose, which is equals to C times D times C transpose, where D is a diagonal matrix whose diagonal elements are the eigenvalues lambda 1, lambda 2, lambda 3, and so on until lambda D. This is called the spectral decomposition of S. Since C is orthogonal and CC transpose is equals to C transpose times C is equals to identity matrix, we can multiply on the left by C transpose and on the right by C to obtain that C transpose times S times C is equals to D. And we know that if Z is equals to W transpose times X, then covariance of Z is equals to W transpose times S times W, which we would like to be equal to a diagonal matrix. Then from equation 6.11, we see that we can set W equals to C. Let us see an example to get some intuition. Range 1995. Assume we are given a class of students with grades on 5 courses and we want to order these students. That is, we want to project the data onto one dimension such that the difference between the data points become most apparent. We can use PCA. The eigenvector with the highest eigenvalue is the direction that has the highest variance. That is the direction on which the students are most spread out. This works better than taking the average because we take into account correlations and the differences in variances. In practice, even if all eigenvalues are greater than 0, if the size of S is small, remembering that the size of S equals to the multiplications of lambda I where multiplication is for multiplying all those indexed I starting from 1 to d, all d dimensions, and we understand that some eigenvalues have little contribution to variance and may be discarded. Then we take into account the leading k components that explain more than, for example, 90% of the variance. When lambda I are sorted in descending order, the proportion of variance explained by the k principal components is lambda 1 plus lambda 2 plus lambda 3 and so on plus lambda k divided by lambda 1 plus lambda 2 plus lambda 3 and so on plus lambda k and so on plus lambda d. If the dimensions are highly correlated, there will be a small number of eigenvectors with large eigenvalues, and k will be much smaller than d, and a large reduction in dimensionality may be attained. This is typically the case in many image and speech processing tasks, where nearby inputs in space or time are highly correlated. If the dimensions are not correlated, k will be as large as d, and there is no gain through PCA. Screen graph is the plot of variance explained as a function of the number of eigenvectors kept. See figure 6.2. By visually analyzing it, one can also decide on k. At the elbow, adding another eigenvector does not significantly increase the variance explained. Another possibility is to ignore the eigenvectors whose eigenvalues are less than the average input variance. Given that the summations of lambda I summing for all index I is equals to the summations of si squared summing for all index I equals to the trace of s denoted as tr of s, the average eigenvalue is equal to the average input variance. When we keep only the eigenvectors with eigenvalues greater than the average eigenvalue, we keep only those that have variance higher than the average input variance. If the variances of the original xi dimensions vary considerably, they affect the direction of the principal components more than the correlations, so a common procedure is to preprocess the data so that each dimension has mean 0 and unit variance before using PCA, or one may use the eigenvectors of the correlation matrix R instead of the covariance matrix S for the correlations to be effective and not the individual variances. PCA explains variance and is sensitive to outliers. A few points distant from the center would have a large effect on the variances and thus the eigenvectors. Robust estimation methods allow calculating parameters in the presence of outliers. A simple method is to calculate the Mahalanobis distance of the data points, discarding the isolated data points that are far away. Figure 6.2. A screen graph B proportion of variance explained is given for the opt digits dataset from the UCI repository. This is a handwritten digit dataset with 10 classes and 64 dimensional inputs. The first 20 eigenvectors explain 90% of the variance. In the first two principal components explain a large percentage of the variance. We can do visual analysis. We can plot data in this two-dimensional space, figure 6.3, and search visually for structure, groups, outliers, normality, and so forth. Figure 6.3, opt digits data plotted in the space of two principal components. Only the labels of 100 data points are shown to minimize the ink-to-noise ratio. Now, this plot gives a better pictorial description of the sample than a plot of any two of the original variables. By looking at the dimensions of the principal components, we can also try to recover meaningful underlying variables that describe the data. For example, in image applications where the inputs are images, the eigenvectors can also be displayed as images and can be seen as templates for important features. They are typically named eigenfaces, eigendigits, and so forth. This is Turk and Pentland reported in 1991. When D is large, calculating, storing, and processing S may be tedious. It is possible to calculate the eigenvectors and eigenvalues directly from data without explicitly calculating the covariance matrix. Chatfield and Collins, 1980. We know from the equation 5.15 that if X is approximately by normal distribution MD of mu sigma, then after projection W transpose times X, which is approximately by NK of W transpose times mu, W transpose times sigma times W. If the sample contains D variate normals, then it projects to K variate normals, allowing us to do parametric discrimination in this hopefully much lower dimensional space. Because Zj are uncorrelated, the new covariance matrices will be diagonal, and if they are normalized to have unit variance, Euclidean distance can be used in this new space, leading to a simple classifier. Instance X transpose is projected to the Z-space as Z transpose equals to W transpose times X transpose times mu, when W is an orthogonal matrix such that W transpose is equals to I. It can be back projected to the original space as X hat transpose equals to W times Z transpose plus mu, and X hat transpose is the reconstruction of X to the transpose from its representation in the Z-space. It is known that among all orthogonal linear projections, PCA minimizes the reconstruction error, which is the distance between the distance and between the instance and its reconstruction from the lower dimensional space. That is, the summations of the distance between X hat to the transpose minus X, then to the square, summing for all in Xt. The reconstruction error depends on how many of the leading components are taken into account in a visual recognition application. For example, face recognition, displaying X hat to the transpose allows a visual check for information lost during PCA. PCA is unsupervised and does not use output information. It is a one-group procedure. However, in the case of classification, there are multiple groups. Carhunen-Loewe expansion allows using class information. For example, instead of using the covariance matrix of the whole sample, we can estimate separate class covariance matrices, take the average weighted by the priors as the covariance matrix, and use its eigenvectors. In a common principal components, this is proposed by Fleury, 1988, we assume that the principal components are the same for each class, whereas the variances of these components differ for different classes. That is, Si is equals to C times Di times C transpose. This allows pooling data and is a regularization method whose complexity is less than that of a common covariance matrix for all classes, while still allowing differentiation of Si. A related approach is flexible discriminant analysis, which does a linear projection to a lower dimensional space where all features are uncorrelated and then uses a minimal distance classifier.